Hello everyone, this is Aksa and I welcome you into the lecture 2 of the Introduction to Azeotropic Distillation. So previously we've just learned about what is azeotrope and how it forms and so on. In this particular lecture we're going to see the thermodynamics, a little bit of a binary system including the azeotrope binary system, and then we're going to introduce to the strategy to break the azeotrope. First, I'd like to show you back a few equation of state models that we normally use for our thermodynamics calculation. So in this equation of state, basically showing us a relationship between molar volume, temperature, and pressure, which is shown in the PVT equation of state. So there are many equation that has been proposed, of course, and the simplest one is the ideal gas law. However, we want to describe many system with a good equation of state. So in here you can see Redlich-Kwong-Swaff or Peng-Robinson. You also hear about before van der Waals equation. However, this equation is rarely used now because the application is quite narrow. So most of the time now we either use SRK or Peng-Robinson. In the equation of state, sometimes we have to determine first a few constant, one or two constant. For example, in generalized equation of state, we need to determine the Z value or the compressibility factor. And then of course we also have A and B constant that we normally use in Redlich-Kwong-Swaff. We can calculate this one from critical data, from critical temperature and critical pressure. And then in SRK or Peng-Robinson, we also need to calculate, we also need to find this eccentric factor. So some of this data or this constant normally available from the table, or you can approximate it using some equation. Since we're dealing with the liquid, especially its highly non-ideal solution, we need to use some empirical equation to estimate some values like activity and also the fugacity. So using this equation, we can definitely predict the properties of the liquid. In here you can see the first three is the one that we normally use at the moment. It's available in most process simulator like HYSYS or Aspen Plus. And then the last one is the van Laar equation, previously used a lot, but now being replaced by the Wilson equation. So you're going to try to practice to use this equation in order to predict the liquid properties for highly non-ideal solution. Here I'd like to show you the data from Sinor and Weber. So this is basically the normal hexane and ethanol system. They are plotted as a y-axis diagram in ethanol, and you can see in here that the equilibrium curve cross the 45-degree line at y equal to x equal to about 0.332. So the temperature corresponding to this composition is around 58 degrees Celsius. So this is a minimum boiling azeotrope for this mixture at 1 atm. So the azeotrope temperature is basically lower than the normal boiling of ethanol, which is about 78.3, and also the normal hexane at 68.75. So the azeotrope occurs because of the close boiling points of the two species and the high activity coefficient for ethanol at low concentration. I'd like to add in here that at the azeotropic composition, when y equal to x, therefore the k value is going to be equal to 1, and a separation cannot be made by a single or multi-state distillation. So we have to use another method to break the azeotrope. So now let's try an exercise to do a calculation of binary interaction constant for the Wilson model. So in here we're going to use the azeotrope data that occur at XE 0.332 and XH of 0.668 at the temperature of 58 degrees Celsius. So if we have this constant, then we can plot the activity coefficient curves. We can predict this one by ignoring the temperature variation of the binary interaction constant. To calculate the binary interaction constant, first we need to calculate the activity coefficient for the ethanol and hexane. So we have to use the data that we have, which is the vapor pressure at that particular condition, and then after getting the activity coefficient, then we can use Wilson equation to predict or to calculate the binary interaction constant. After obtaining both constant, then we can now use that constant to predict the activity coefficient for the entire system. So in here we can see the comparison between Van Laart and also Wilson. We can see that Wilson curve are almost identical to the data, which is compared to the Van Laart a little bit difficult to predict at the dilute region. Here we have another set of data of benzene and cyclohexane system. So I want you guys to practice to use the Van Laart equation and also Wilson equation and compare both of them. Try to do the calculation to plot the relative volatility of benzene with respect to cyclohexane, and then we're going to use this one to calculate the constant, the interaction constant, and then later we can use it to produce a similar graph that we have in the previous practice. Here I provide the solution for the particular question that we have in this practice. So at first you have to do the calculation of relative volatility, and then after that use that one to find the interaction constant, binary interaction constant, and then use the Van Laart equation that you have to do the calculation of the activity coefficient. And then of course you can also use the Wilson equation that we just learned. So using this calculation, I hope you can compare later the results between the Van Laart and Wilson one more time. Now let's talk a little bit about a few strategies or methods that we can use to break the azeotrope. The first one is the pressure swing distillation. So in this method we don't use any entrainer or separating agent. Normally some binary azeotrope mixture they can lose their azeotropic behavior when the pressure of the system is changed. So in here we're utilizing the pressure swing distillation to separate the pressure sensitive mixture with close boiling point or forming azeotrope. As you can see in the figure on the right side here, so what we do during the pressure swing distillation, you can have two different columns where you have high pressure column and also a lower pressure column. So in both of them you can completely have a different product at the top just to kind of break the azeotrope. And then the other method that we can use is the homogeneous azeotropic distillation. So this method basically using an entrainer that form a homogeneous minimum or maximum boiling azeotrope with the feed components. So where the entrainer is added depend on whether the azeotrope is removed from the top or the bottom of the column. And then we can also have the heterogeneous azeotropic distillation, which is much preferable. So in here we're going to have a mixture that heterogeneous, and then this azeotrope splits into two liquid phases in the overhead condenser. So it's easy to separate So one liquid phase is sent back to as a reflux, and then the other one is sent to another separation step or taken off as a product. And then the last one is the reactive distillation. So in here, it's involved the addition of chemical that react selectively and reversibly with one or more feed constituent.